AP Calculus BC, Unit 5, Day 3, Lesson, Differential Equations. So we're going to use some of the new stuff, some of the stuff we've been reviewing, and also some of the new stuff from the last lesson with differential equations. So this is a bit of review of solve differential equations, and we'll use it for a couple applications that we saw last year. I mean, one was exponential growth. So just real quick, exponential growth kind of looks like this, right? It goes through 0, 1, has a horizontal asymptote, y equals 0. That's the exponential curve. Now, the definition that you may have even seen in, like, say, an Algebra 1 book would be like the rate of change is, or the growth rate is directly proportional to the current amount or current population. So directly proportional, okay, is would be an equal sign. So the rate of change of the growth rate, well, that's a derivative, right? This right here is talking about a derivative in our current terms. You could say like dy dt. Often it's time on these problems is directly proportional. K is constant proportionality. The current amount, which is y. This is the definition of exponential growth written as a differential equation derivative. This is the constant of proportionality. So we learned last year in Calc AB how to solve differential equations. So let's see if we can do that. And that's something we're going to be doing on the current assignment. So what we have to do is we have to separate the variables. Got to get the y with the dy, and you got to get the dt or dx, or whatever it was, out of the denominator. So we split it up. It's called separating the variables. Because you're getting all of one kind of variable with one. The k is just a number. So then we integrate both sides. So we have two antiderivatives. The antiderivative here would be natural log of the absolute value of y equals over here. So it's going to be kt plus c. Got to do plus e. Now, a lot of times you have an initial condition that you can plug in, so you can find c value right away. Otherwise, we're just going to drag it with us. Now we got to get y by itself. So we're going to exponentiate both sides. Yeah, we have absolute value of y. Absolute values are still there. E to the kt. And we could change it to times e to the c, rules of exponents. And then to get rid of the absolute values, you got to do plus or minus. Now, e to the c, let's just call it c. You can call it c2 if you want. If it bugs you, I would just call it c. It's just another constant. And for us, the plus or the minus will get figured out based off the initial condition. But a lot of times what we do is we say this initial condition, if you plug in t is 0, this goes to 1, and you get this, which would be your initial population. So a lot of times we refer to that with y sub 0. And sure enough, we got the general model for exponential growth. So that's something we did before. Now let's do something new, logistic growth, which I think I mentioned last year in Calc AB, and some of you guys have seen it in like biology and other courses. And it's more realistic growth model. Growth generally for most things is not just unbounded and just keeps getting bigger and bigger and bigger. There are things like room, resources, food, predators, all kinds of different things that will prevent something from just growing unbounded. You know, if it's a disease, there's only so many people that can be infected or whatever. So logistic growth looks more like this. It has a horizontal asymptote down here at y equals 0, but then it has another one up here, y equals m. Capital M is what we usually use. This is called the carrying capacity. And that's a term I believe you've heard in other classes. Carrying capacity. Essentially, it's the upper bound. It's the ceiling. At first, now something special happens at half the carrying capacity. At first, growth is exponential when the population is small. But then it bends back down, concave down, towards the carrying capacity. Now, what happens is once you hit half the carrying capacity, you have an inflection point. which is also where the growth is the most steepest slope. So that's what the graph looks like. But we can use that idea to help us kind of understand what the differential equation, we got dy dt equals ky for exponential. Here it's going to be dy dt, and it will have the ky component of it because at first it is exponential. But then it has this other thing, so it has this exponential part. But then it has this other part that makes it bend down as the population gets close to the carrying capacity. So it's the carrying capacity minus y. So when y is small, then this just gets wrapped up into the k value. It's all exponential. When y gets close to m, this gets really tiny and makes the whole thing get tiny. As y gets closer to m, the whole thing goes to 0, which makes it flat. So I'd call this like the limiting factor. So that's what the differential equation for logistic growth looks like. The limit as t goes to infinity, whether the growth rate goes to 0, right? That's what we're saying. It gets flat. You run out of room to grow, so you grow very slowly when you approach that. Now, let's see if we can find the solution to the logistic differential equation. Let's find the model for logistic growth like we did for exponential over here on the left. Now, this is going to be a bit more complicated, though, and it's going to require some of our new skills. And by the way, logistic growth is on the AP Calculus BC exam. It is a subject. So we need to separate the variables. We have the dy. Let's bring the y and the m minus y over to the left. The m is just a number. I personally would leave the k and any other constants on the right because it's easier to deal with them over there, less moving around. You have to get y by itself eventually anyways. Now, what you should realize is that right away we're doing partial fractions, right? So this is going to be a over y plus b over m minus y dy. And I'm just going to leave the right side like this. So we've got to take a little break for work right here. So it's 1 over y m minus y equals a over y plus b over m minus y. So we need to multiply through by the least common denominator. So we can get 1 equals a m minus y plus b times y. Use the heavy side approach, cover up method. Plug 0 in first. And you get 1 equals ma. So a equals 1 over m. You could plug m in to make the a term drop out and get 1 equals mb. And b equals 1 over m. It's kind of interesting. They came out the same. Right? Now, these are the coefficients. M is just a number. So when I rewrite it over here, it's going to be 1 over m dy over y plus 1 over m dy over m minus y equals k dt. So this is going to be 1 over m natural log of the absolute value of y plus 1 over m natural log of the absolute value of m minus y. Now be careful. There's an extra negative here. The chain rule is going to pop out, so we need an extra negative right here. That is an easy mistake people make on this test. On any time you just watch out for that minus. Okay, equals kt plus c. We only need c on plus c on one side. So now we need to solve for y. So this is where this gets extra messy. So I would multiply both sides by m. Okay, and then I'd use log rules to combine these guys together. So it's going to be natural log of y over m minus y equals mkt plus mc is just still a new constant. So I'm just going to write c. Now we're trying to get y by itself, so then we exponentiate both sides, right? And then we also can get rid of the absolute values, plus or minus, and e to the mkt times e to the c rules of exponents. We can break that up. Now I'm just going to call that a new c again. Now we're going to go ahead and go with the positive. Like I said, the initial value will get brought into it. But so now we need to multiply both sides by m minus y and distribute. So y equals m c e to the mkt minus y c e to the mkt. And then we want to get the y's back together on the same side. We didn't want them in a fraction though. That's why we had to bust everything up. But now we can bring this back over here and factor the y out. There's 1 plus ce to the mkt equals mce to the mkt. Getting close. So we're going to divide both sides by that. And now we're going to manipulate this a little bit to make it look like a memorized version. So what we could do is we could, this is what we're going to do. We're going to multiply by 1 over ce to the mkt top and bottom, which we're allowed to do with fractions. Multiply top and bottom and divide the top and bottom with the same thing. Now, when you do that, it gets rid of this guy. And so now we have m over 1 over ce to the mkt plus c, actually plus 1, and one more little twitch. We're going to change this to negative exponent. We're going to lead with the 1. So this is the memorized version. M over 1 plus, now 1 over c, I'm going to give a new letter called a. That's just what they use. E to the negative mkt. So this is the version of logistic growth that we will be using. This is the model. Okay. And we just derived it. It was a bit of work and had a little extra manipulation at the end. Good news is you don't need this, you don't need logistic growth yet. We will come back to next semester. But the skills we used to derive this, we're going to need for the current chapter because it was a bunch of partial fractions. On the back, we have one more example of solving a differential equation and having to make use of some of our new skills. Now, remember, when you solve differential equations, you're required to put the domain with your answer. The domain's a little tricky. It's based off of the basic domain, but it's also based off of a single open interval where the function is defined and also where the derivative is defined, and it uses the initial condition to find it. So why don't you guys see if you can try this problem, separate the variables, solve the differential equation. So we're going to separate the variables. With the y's with the, now here's the deal. You want to leave this factored and leave the 2x on the right side. I would say it'd probably be the strategy. So it's going to be dy over y 2y plus 1 equals 2x dx. That's probably the way I would do it. You bring the 2 to the left side, but that's just going to make it more complicated. Now we got to do partial fractions here, right? So, by the way, this is not logistic. I mean, it looks close, but We have an initial condition here, so we're going to use that to find the c value when the c pops up. So we got to do partial fractions. So this is going to be a over y plus b over 2y plus 1 dy. And so we're going to, if we multiply 3 by the least common denominator, it's going to be 1 equals a 2y plus 1 plus b y. And we could get rid of the b, plug 0 in, a equals 1. We plug in a negative 1/2 to make the a go away, and then we get a 1 equals negative 1/2 b, so b equals negative 2. So left-hand side is going to become dy over y minus 2 dy over 2y plus 1 equals 2x dx. So now we're ready to integrate. So this is going to be natural log of the absolute value of y minus 2. This is going to be natural log of the absolute value of 2y plus 1, but an extra 2 is going to pop out that we don't want, so we have to divide by 2. All right, chain rule. There was already a 2, so it works out nice. This is going to be x squared plus c. Now, before we find the c, I'm going to combine these together. Natural log of y over 2y plus 1. I don't know. Seems like that'd be easier. So let's use initial condition. Y equals 1 when x equals 0. So c equals natural log of 1/3. Or negative natural log of 3. If you want to think of it as 3 and negative 1, bring the power up front. So either one. Okay, so now we need to rewrite it with the c value in there. I'll go ahead and just leave it as the 1/3. So now we need to solve for y. Got to exponentiate both sides. Got to get rid of the absolute values. Plus or minus. It's going to be e to the x squared times e to the natural log of 1/3. Rules of exponents, you break them up. Which, that's going to just give you a 1/3. So then we want to multiply the 2y plus 1 to the other side. Now, we need to decide if it's plus or minus. Now, remember when you plug in 0, you should get a positive 1 out. So if I plug 1 over here, that's going to be 1/3 equals plus or minus e to the 0 times 1/3. We want the positive. So that's going to be 1/3 e to the x squared. I would distribute it. So we've got to distribute all this and then bring all the y's back together on the same side. I don't want all the y's on one side like this and a fraction on the top and bottom. That doesn't work. So it's going to be 2/3 y e to the x squared plus 1/3 e to the x squared. So now we can bring our y's together on the other side. And then factor the y out. That's sort of how we combine like terms when they don't really have like coefficients. And then we can divide both sides by 1 minus 2/3 e to the x squared, 1 minus 2/3 e to the x squared. I don't want complex fractions, so we're going to multiply by 3. That should take care of it. So y equals e to the x squared over 3 minus 2 e to the x squared. You also need to state the domain, okay? So on these problems, essentially it's where can I use this solution, which depends itself, like Are there any issues with the domain of the answer? Well, we can't divide by 0, so let's see if we can figure out what value of x would make that happen. So 2e the x squared equals 3. Take the natural log of both sides. All right, and we get x squared. So then we have to take the square root of both sides, plus or minus both of those. So we get these two values. Now, natural log of 3/2 is definitely positive, so that should be fine. We should get two real answers. Is there any other points? So like, you also have to go back to the original differential equation and say, are there any x or y values that would make that undefined? Because that matters too. This time there isn't. Nothing causes division by 0 or natural logs of negatives or square roots of negatives or whatever. So we're good there. Nothing else. It's just this. So what we do is, these are actually easier to do domain than if I just gave you this and I said, what's the domain? It'd actually be harder than this. You would do all this, but these are going to be open dots. One's going to be negative, and one's going to be positive. And instead of having to do a whole line test, we just take the initial condition, which is 0, which would need to be between these, and that's the chunk. That's going to be your domain. Even if other values over here work, that's all we want. Single open interval no matter what, right? So, I mean, x can't be 0 anyways, but even if it could, we would leave it out. So the domain is negative square root of natural log of 3/2 to square root of natural log of 3/2. So you have to provide the domain with the solutions of differential equations. Otherwise, you do not receive full credit. Okay, assignment, page 369, 8 to 20 all. Check your odds in the back of the book. I'll post the evens if I have them available, and try these problems. Mostly today is, it's a review of solving differential equations, but also using some of our new integration techniques, partial fractions, etc. Everything's fair game. So try it out.